Hey everyone, and welcome to the channel. And thank you so much for being here. The channel grew substantially, and now we are over 50 subscribers, which is great and amazing. And thank you so much for that. Today, I'm in Santiago, Chile, where I was kindly invited by my employer, the company called TopSort, and we are building the ad system, a new generation ad system for marketplaces, and we are hiring. So if you are interested in joining us, and you have background in machine learning, please message me on the LinkedIn and I will put the link to my profile in the description of this video. And today I want to talk about a topic that is not exactly the auction theory topic, but it's a machine learning topic. Very importantly, in ad systems, we need to be able to predict click-through rates and conversion rates. And today I'm going to talk about one trick that I learned many years ago. And that the trick is an amazing thing and it helps so much and it's so useful. But I was puzzled for a long time. I was puzzled why it works. And today I'm happy to tell you that I figured it out and I'm going to explain it with a lot of details. So let's jump into that. The topic we are going to talk about is called the exponent activation function for conversion rate learning. And this is about the activation function of the output layer. Typically for click-through rate and conversion rate prediction, the activation function would be a sigmoid because we would map the raw output of a learning model, such as a neural network. We would want to map it to the space of valid probabilities. And this is achieved by applying a sigmoid function that would map the raw prediction to the range of from 0 to 1. But in fact, uh, in many applications, it is possible to use binary classification setting and binary classification loss. But at the same time, it could be possible that the outcome that is predicted or modeled by the model uh, does not need to be constrained to the range from 0 to 1. And even as the name suggests, we are talking about the rate of conversion. And the rates of conversion could be larger than 1, like no problem. It could happen that there are more clicks than impressions or more purchases than clicks for like the case of conversion rate. And to give you a motivating example, here is a very famous paper, Deep Neural Networks for YouTube Recommendations. And this is a great and amazing paper from, I think, around 2019. And in this paper, they give a lot of information, very valuable information about how the YouTube recommendations work. And in general, they cover both stages of like a full-blown recommendation system, which is a retrieval stage and the ranking stage. And I'm not going to cover the whole paper here, but I just want to focus on one single topic in that paper, which is about the target that they use for ranking, and that target is the watch time. And they still apply the binary classification loss, cross entropy essentially, but they use weight to to train the model to predict expected watch time. And depending on how they normalize watch time, we could expect that the watch time measured maybe in seconds could be like arbitrary, and then the rate, essentially the conversion rate in this situation would be number of seconds per click or number of seconds watched per impression, something like that. So let's actually read what they have to say in this paragraph. This paragraph is pretty short. So our goal is to predict expected watch time given training examples that are either positive, the video impression was clicked, or negative, the impression was not clicked. So they are talking about click-through rate on the video recommendation snippets. Positive examples are annotated with the amount of time the user spent watching the video, and to predict expected watch time, we use the technique of weighted logistic regression, which was developed for this purpose. And I want to emphasize that we are going to see in the next paragraph how it works and how they did it. And the trick I'm going to talk about, they don't know about it. So they're doing something different, and we will see where is the connection. Let's keep going. The model is trained with logistic regression under the cross entropy loss. So what is that? Well, basically, this is the most common binary classification loss. Let's assume that we have our labels, yi's, which are binary labels, zeros and ones. And then if the value is 1, the label value is 1, we also have the watch time, which is ti. So the watch time is maybe measured in seconds. So then the loss that they use to do here is essentially the sum of all examples independently. This is like a log loss. This is like the negative log likelihood. And the original log likelihood would be yi's log pi's, where the pi is the probability, plus the 1 minus yi log 1 minus pi. And the pi is this model, which would typically be a sigmoid of, this is like the final layer activation function, the sigmoid applied to the output of the neural network, which we're going to call f. And that f depends on the weights of the neural network w and the features of this example xi's. And well, of course, the task of the learning procedure is to come up with a good or maybe optimal set of weights of the neural network. Now, the twist that they add to this is that they introduce the weights for the watch time, and they only apply those weights to the positive examples. So here we go. They apply TIs here, and essentially for the negative examples, the TI is just set to 1. Or maybe like it's implicit here that it's multiplied by 1. This is what I mean. So let's keep reading. So they say negative unclicked impressions all receive unit weight. Yes, exactly as I said. And in this way, the odds learned by the logistic regressions are sum over TIs. Okay, they used capital TI and I used lowercase ti, but it doesn't matter. Over n minus k, where n is the number of training examples, k is the number of positive impressions, and ti is the watch time of the impression. So let's see how we could derive that. First, we need to simplify this a little bit, because they are what they are saying here is that, well, what if we don't have any features, and what if we just want to train like a single probability, like the single average probability? Then, well, maybe we would say that pi is actually like we don't have any way to distinct different examples, so all the pi's are equal to some common value p. And to find that optimal p, we would do dl over dp equal to 0. So this is the first order optimality condition. And now we need to take the derivative with respect to p. And we could also assume that p, this is going to be helpful a little bit later. We are going to assume that p is a sigmoid of some f and that f doesn't have features now. So this f is just a constant. So let's take a derivative with respect to p. We are going to have sum of tiyi's over p minus, and this minus comes from this chain rule differentiation here. So we are going to have sum over all examples of 1 minus yi's over 1 minus p, and all of this is equals to 0. So what they say here, they say that the odds are given by this expression. So, well, the odds are p over 1 minus p. This is the definition of the odds. So the odds are p over 1 minus p, and we can see that, well, this is the sum of ti times yi over the sum of I1 minus yi, and this is equal to the total watch time, t, divided by n minus k, where n is number of impressions, and k is number of clicks. So what they do next, they say that, well, first of all, the number of clicks is small. So we can approximately assume that this is just an average watch time, t over n, which is like an expected watch time of individual watch example. But now what they do is they turn their they look at this ratio, and they just remember that we said that p is going to be a sigmoid of f. And using the explicit formula for the sigmoid, we will see how this transforms. So this is going to be e of f, e to the f over 1 plus e to the f. So this is the definition of the sigmoid. And now if we substitute that into the formula for the odds, we get that p over 1 minus p is going to be e to the f over 1 plus e to the f divided by 1 minus e to the f over 1 plus e to the f. And now by rearranging terms a little bit here, we get e to the f here, the same stuff. But at the bottom, we are going to get 1 over 1 plus e to the f. So these denominators cancel, and we end up with e to the f. And this is exactly what we now have. So this stuff is e to the f. And okay, let's write it once again here. So e to the f is approximately proportional to the expected watch time. So going back to the top, to summarize what happened here, they used logistic regression with weight to train a model using standard pretty standard binary classification logistic loss or negative log likelihood for logistic regression, the same thing as the cross entropy. And given that the expected number of clicks is actually small, they see that this approximately results in this gives them the way to model the expected time as an exponent of the learned raw output of the neural network. So now I'm going to explain a trick, and it's a very small modification of the learning procedure. Unfortunately, I don't exactly know who invented the trick, but I don't claim that I invented the trick, and the credit for this trick belongs to the person who invented it. So let's see how this trick works. So we need to take a closer look at the data set that we have for our training. And okay, so the column with the header I, with the name I, is just the number of the example. Then the Y as is the binary label. So this maybe is a impression, and it didn't happen to be a click. And then we have the watch time, which we would put the wait for the watch time as in the YouTube example, we set it to 1. Then we have Y. Let's think that let's assume that the example number 2 is a click, and the corresponding watch time is, let's say, 25 seconds. And then we have another impression without a click, and maybe another impression without a click. So this S variable here, S column here, I'm going to explain it a little bit later, but for now, we will just assume that this is going to contain 1 for every impression. So this is going to be 1, 1, 1, 1, and we will talk a little bit later about how we can use this column S to get additional flexibility here. And then the columns x1 to xm are just the features of the examples. So this could be a user ID, a video ID, the time of the day, whatever, all possible features that we could come up with. So the idea of the trick is to find the rows that are clicks. So for example, this row is a click. We have a click here. And duplicate this rule with by like copying the features. So this is going to be x1, for example, number 2, x2, for example, number 2, etc. Xm, for example, number 2. So we need to copy this. So we are going to copy this exactly like this. So same features, but we are going to put a 0 for the label, for the target. We are going to put 1 here, and we are going to put 1 here. So really what happened here is we said that let's just take a click and copy it by adding an impression with the same feature. And let's do this for all clicks in the dataset. So what is this? Why is it useful? First, it's easiest to see what happens to the loss function. So remember, we had the loss function here, which was the sum of I, and I'm dropping the minus sign from here because it's not important. We had yi ti log p I plus 1 minus yi log 1 minus pi. But now, because we added a negative example here, this negative example, for every positive example, we can see that whenever yi was 1, this thing used to be 0. But now, because we added another example with this with the label 0, we are actually going to get rid of this y. Oh, sorry. We are going to get rid of this yi here. This is this is the whole the whole idea of the trick, to introduce the copies here just to cancel the yi's here. And the sum still runs over the original example. The sum is still over yi's. So maybe we should give this the number to prime or something like this to see that we still keep the sum over the same number of original rows, and this copying could be simply interpreted as removing the yi from here. Okay. So now let's see what is going to happen with the in this case. And again, for the sake of like simplicity, we are going to drop the I from the P. We are going to model the P as a sigmoid. Sigmoid. Let's do P prime just to make sure that this is a different P from the one that we had previously. And this is the PI that is obtained by training a weighted logistic regression on a modified dataset. So this P prime is now a sigmoid of some F prime, and we are going to see what's the relation here. Well, once again, I guess the loss itself should be prime because this is a different loss. So we do dl prime over dp prime equals to 0. So this is again the optimality condition. And we get sum over yi ti over p prime minus, well, now we only have 1 here. So it's going to be 1 over 1 minus p prime. And from here we see that p prime, oh sorry, this is going to be the sum of ones, and the sum of ones is the number of original examples, the number of original impressions. So this is the sum of 1, and this is equal to the original number of examples n. This is the watch time t. So p prime over 1 minus p prime is going to be t over n, or expected watch time t. And exactly by the same computation, now we have that p prime used to be a sigmoid of f prime. So now this thing is going to be equal to e to the f prime. So we get e to the f prime equals to expected watch time. So we get the same result. But the difference is that there is no approximation here. We don't need to assume that the number of clicks is small compared to anything. So this is exact. So what's the connection between two methods? Both methods gave us the same result, but one of them is approximate and the other one is exact. Well, the connection is very simple actually. If we draw a sigmoid, this is the f, and this is the sigmoid of f. The plot looks something like this. And if we draw exponent, we would see that in the range of large negative f's, the exponent and the sigmoids, they are the same function, and they diverge closer to 0, where the exponent crosses 1 and goes there up there. So this is clearly seen by sigmoid of f being e to the f over 1 plus e to the f. And when f is large negative, so when we consider f going to minus infinity, this is going to be e to the f is going to be a very small number compared to 1. So we can drop this thing here. The e to the f is small compared to 1. So 1 is much, much larger than e to the f. And then this is approximately equal to e to the f. And this is the connection between those two methods. Essentially, the method from the YouTube paper works because this approximation is valid for large negative values of f. So this trick allows us to model the click-through rates and conversion rates with an exponent link function. This is extremely useful for auctions. This is because auction theory for search ads, for example, the basic model of a theory, the slot auction, it assumes that the click-through rate could be factorized in two multipliers. One of the multipliers would be the banner or the ad contribution, and when the ad is placed in different slots on the page, the change in the CTR could be modeled by a multiplicative correction that depends only on the slot. So modeling these multiplicative contributions is quite hard with sigmoids, but very straightforward and very easy with exponents. The second reason is that no assumption in auction theory is made about the click-through rate or conversion rate should be a proper probability normalized from 0 to 1. I already mentioned this at the start of this video, but I just want to reiterate on this. And modeling the rate with an exponent link allows allows us to model the click-through rates and conversion rates as rates, and there are no constraints that there couldn't be more clicks than impressions or more orders than clicks, or the watch time needs to be normalized in a way that would allow to assume that it is small compared to some number. Finally, there is a technical reason why modeling with this trick is so nice. Is that when we are doing this trick, we are basically we are basically copying the click and making an impression out of it. But in reality, or like most of the times, it's the other way around. It's very usual that we get the impressions first and then we get the clicks separately because there is some delay between the click and the impression. So we register the impression when the ad or the snippet of the video appears on the user screen. But then clicks and watch times they are registered separately later when there is the interaction happening, and they are reported through different channels. They are reported through different channels, and then there is some procedure that needs to be done to actually join them back to find the source impression for this click or to find the source click for this order, and those are complicated things. If we look at the trick as the split of things, this copying of things, that well, in reality, we have the original data actually presented in this splitted way. It still requires us to somehow figure out how to find the features for impressions and the features for clicks and the features for orders or the features for the events where the video was watched for a given amount of seconds. But still, this is very, very natural for how the data is actually collected. So now let's see what this trick actually does. Now we will see that this transformation, the transformation of splitting the positive examples into and making a copy of a positive example with a negative with the same features but a negative label could be interpreted as going from maximum likelihood estimation for Bernoulli model to something that is called negative binomial regression. I will give more background on the negative binomial regression in a second, but actually this is even like a special case of the negative binomial regression, where the variance parameter of the negative binomial regression, this parameter is called R, is going to assume a special value. The R is going to be equal to 1, and this results in a negative binomial distribution reducing to the geometric distribution. So therefore, we will see that this is actually this should probably be called the geometric regression. Okay, so let's try to see it, and the way we are going to see it is that we are going to first start from from the basic formulas for negative binomial regression. And then we will see that by using the R equals to 1, we can actually, and by doing the logarithm, treating every example independently and taking the logarithm, we would be able to arrive at the same loss function as we had when we created the copies and therefore canceled the positive labels on this second part of the loss function. So let's see. Let's start with the negative binomial regression from negative binomial distribution. And the negative binomial distribution is usually written by like this. It's the probability of getting k negative events in a series of Bernoulli trials, getting k negative results before getting R positive results. And this is parameterized by the probability of success in a single Bernoulli trial, P. And this could be written as some normalizing multiplier, which depends on the K and R. And then we have P to the power of K and 1 minus P to the power of R. And it's very tempting to try to interpret this P as the CTR, and it just completely doesn't work. So this is not what happens when we do the trick. So to see what actually happens when we do the trick, we need to get a little bit deeper into the idea of negative binomial regression, because it abstracts from this original source of original interpretation of the negative binomial distribution. And the way it works uh, is like this. First, we need to reparameterize just a little bit. We need to relabel. This is going to help us to see like the exact formulas that we want to get. And let's relabel Q equal 1 minus P. So then we can rewrite this as, well, probability of K and given R and P. So I guess the semicolon should go here because R is a parameter. It's going to be written as some normalizing factor, which doesn't depend on P. This is going to be 1 minus Q to the power of K, and then Q to the power of R. With these definitions, the average value, the expected value of K is going to be given by R times Q over 1 minus Q. And then the variance is going to be R times Q over 1 minus Q squared. From this, it is possible to express Q in terms of the mean of the distribution and the parameter R. So let's do that. From here, we are going to see that Q is going to be equal to, let's do it carefully. It's going to be mu 1 minus Q equals R dot Q. And then we have mu equals R plus mu times Q. And therefore we get Q equals to mu over R plus mu. And therefore we have 1 minus Q is equal to R over R plus mu. And now we can also see that variance is going to be, let's just substitute R times mu over R plus mu. And here in the denominator, we're going to have 1 minus q, which is r plus mu squared. So this is r times mu over r plus mu. And down there we have r over r squared over r plus mu squared, right? So now we cancel r. Here we'll lose the square. We cancel this from here. So we get mu times r plus mu over r. And therefore we get mu plus mu squared over r. And the idea is to model the number of the rate. The idea is to model the rate as mu. And now the final step here is to notice that we need to set r to 1. And in this case, we are going to get that the mu is going to be just q over 1 minus q. But originally the r was here. So this thing, we could name it rate per unit, like maybe click per impression. And the interpretation of r is number of impressions. So this is a little bit awkward because it's a little bit backwards. In the straightforward, like a textbook interpretation of negative binomial regression, the r would be the number of successes, and then the k or the mu would be the average number of failures. But to get our likelihood here, we want to set the things the other way around. We want to set the number of impressions to r, and then we want to model the number of successes per impression, number of clicks per impression as q over 1 minus q. And remember that q is 1 minus the probability of success in the original negative binomial regression. So this is like making making everything backwards for negative binomial regression. But when we do this, we end up with a likelihood. So this is for a single example. So we now we can set k equals to yi, and r we set to number of impressions, which we are going to call si. And for now, we are going to assume that this is equal to 1. So now we get the loss function. This loss function is the logarithm of the product of the negative binomials. So we end up with sum over yi log qi plus r, or now we set r to si. So for a second, it's going to be just 1 times log 1 minus qi. And by setting qi equals to p prime, we get the we get the loss function that we got by the trick. So when we did the trick, we split it individual examples into clicks and impressions, or positives and negatives, and we used to model watch times in the watch time example as a weight here. But now we can see that we can now model the amount of success, like the amount of watch time or the number of clicks or the number of orders right here with y. So we can basically keep the multiplication of yi over ti. And also si doesn't really need to be a unit. So this is a small extension to the thing. We can also model this, use this to model the click-through rates or conversion rates or watch times um, by assigning weights to impressions. So this way we could replace um, this one with SI. And interestingly, we would have that now the expected number of successes is going to be proportional to the number of impressions, number of opportunities, times Q over 1 minus Q, where this thing is going to model the rate of success per unit opportunity. And alternatively, this is also called exposure. And also we can see that the variance of this thing, remember it used to be mu plus mu squared over r. We replaced r with si. And we also had a factor of si in mu. So we extract the si, and this is going to be q over 1 minus q. Let's call this like a mu normalized, something this like mu per unit. So this is going to be si times mu per unit I. And here we have si squared, mu I squared, yes, normalized over si. So this one cancels, and we get si outside of this, mu I plus mu I squared. And this is why this is like divided over 1. So this is where we have this geometric interpretation of the thing. So essentially what happened here is that we are modeling this as we are modeling the number of successes or the number of positive things as a geometric distribution in with exposure. So we factored out the number of opportunities or the exposure, and then the number of successes per unit exposure is modeled with the geometric distribution. So this is the interpretation of the trick, and the proof for it is just that we are getting this is exactly the same loss function. So now we can review and like get back a little bit to the data set that we had and finish the video with like a small slight generalization of how we model things now. So we have again the number of the example, the y now, this label is going to contain the amount of positive things that happen. The s is the exposure. And then we have features, x1 to xm. And yes, clearly we can have, in example 1, we could have 50 seconds of watch time for, let's say, 2.5 exposure. So that could be the size of the ad or the prominence of the the prominence of the snippet in some features here. And example number 2 could be maybe 0 successes for 1 exposure, and etc. So when we model this with a loss function that is going to be sum over yi's logs of q, plus si log 1 minus q. The q is going to be modeled as some sigmoid of fi, which depends on the weights of the network and the features of the example xi, and then the rate that we wanted to model, the rate is going to be qi over 1 minus qi, and it's going to be the exponent of f. We don't need I here. Going to be f over the weights of the network, the features, and this is exactly what we wanted to get. To end the video, I just want to summarize that the interpretation of the trick is that this is a negative binomial regression, actually a special case, the geometric regression. But this splitting trick, this idea of splitting rows, allows us to use the weighted log likelihood for binary classification as the loss function, and therefore this trick is actually possible to do with any machine learning tool that supports weighted logistic regression. And it's just a matter of if the data set that you have comes with clicks already joined to impressions, then you would have like the column for success and the column for exposure, and then you actually need to do the trick. You need to split the rows to make it compatible with the logistic loss, and you train for that. So you get the outputs with when you train with sigmoid activations, but when you're making the prediction, when you're making the inference, instead of applying sigmoid to the raw output of the network, you would apply an exponent to get the actual rate that you wanted to model. And when as I already explained, sometimes it's just natural that the data set already clicks separately from impressions, or positive amount of positive thing that happened comes separately from exposure, so they are coming through different channels. Then there is no trick to do, and actually there is no requirement to even do the join. There is no requirement to find the impression that was responsible for this click. The only thing that needs to be done is to find the features. And then the trick is like already there, it's already done. For quite a while, I didn't know that this is actually like pretty straightforward, and this is this geometric regression. And the negative binomial regression itself is a very well-known tool. It's a very well-studied tool. It's available in many statistical packages, and there was a book by Hilbert, 500 pages, all about negative binomial regression and all various parameterizations and applications and connections to the Poisson regression. It's just nice to get this understanding that this trick, it turns the Bernoulli likelihood into this geometric regression thing. That's it. Thank you for watching the video. Please give this video a like, consider subscribing to the channel, and thank you very much, and see you in the next one.